Welcome to the last lecture regarding Unit 3. In the next lecture, we will start discussing Unit 4. To review what we've learned last time, we decided that if there are no external forces, non-conservative forces at work on a system, that the total mechanical energy will be conserved. That is, that the initial total energy, mechanical energy, will equal the final total mechanical energy. One implication of that we didn't discuss last time is that energy can change forms in this total. So remember that mechanical energy is defined to be the total of kinetic plus potential. And that potential could take on different types of potential energy. We discussed gravitational potential energy and elastic potential energy. You could add in any other potential energies that might be going on in your system. At any point in time, though, you might have more of this and less of this, for example. Later, you might have more of this and less of this, because the energy might have changed forms between, say, kinetic energy and potential energy, or vice versa. Another implication of this idea of conservation of mechanical energy is that when we have a closed system, energy cannot be created or destroyed. In other words, it can't just disappear out of nowhere or appear out of nowhere. And so that's why whenever we had the external forces, so non-conservative forces, doing some sort of work on the system, then that work is going to equal any change of mechanical energy. Because we can't have that mechanical energy disappear, it has to be accounted for somehow. Okay, so that recaps everything that we discussed last time, and we did a lot of examples where we applied these principles to problem-solving situations. I want to do one last example that's more conceptual for you and introduce an idea of an energy graph. So let's say, for example, that I've got a bowling ball hanging from a cord which is attached to the ceiling, and I raise the bowling ball up some height h, just like we did with the person swinging into the water. So you may be raised up a certain height that has to do with your angle away from the vertical. Okay, but in raising this bowling ball a certain height, I've now given it some sort of potential energy related to gravity. I can imagine creating a graph in which I try to quantify the amount of different energies. So I'm bookkeeping the situation in terms of how the energy is transformed and how much of it there is at one point in time versus later. At this point in time, where I'm just holding the bowling ball here at this height h, the only thing going on is that I've got potential energy stored in the bowling ball. So in this energy graph, I'm going to create a bar which represents the total energy, potential energy that I have, which would be mgh. And that's the sum total of my mechanical energy in the system. If I ignore any work done by friction and say that that's negligible, then when I let go of this bowling ball, you can imagine that this potential energy which I've stored is going to be transformed into kinetic energy of motion as the ball falls. So a question might be, what will happen if I take that bowling ball and stick it right beside my face and then release the bowling ball? And you might wonder, will it come back and hit me in the face or not? I have a separate YouTube video that's linked right here, which you can look at me actually doing this demonstration. I can't actually do it from remotely for you, but that is recorded for posterity that you can look at it. And if you fast forward to this time that I have indicated there, you'll see exactly what happens in answer to this question. But if we go through the logic of what's going on, we can create a conclusion here. We can come to a conclusion here. So at the very first position, I had in my energy graph only potential energy as the bowling ball was at rest, and I had nothing in the kinetic energy column. Once I release it, some of that potential energy will be transformed into kinetic energy of motion as the ball falls. At some other point, when it reaches its lowest point, there will no longer be potential energy stored. All of that would have been transformed into kinetic energy. And importantly, if we say that no work is done by friction or air resistance, if we ignore all of that, then this kinetic energy bar should be the same height as the initial potential energy bar that I started with. So maybe you can see now where I'm going with this. Later on in the ball's flight, it will go back to this situation where I have some potential energy as it rises up again and some kinetic energy as it's still moving. And then when it gets to the other side, it will have only potential energy again in the same amount that it started with. So if I reverse these actions as it comes back towards me, I can conclude that there's no way for this ball to ever reach a greater potential energy, i.e. a greater height, than what it started with. So even though it may feel scary to me, as long as I start it off from rest and let go of it right beside my face and don't move, it should not come back and hit me in the face because it cannot go any higher than what it did to start with. Okay, notice that I said though that I let go of this bowling ball from rest. What would happen if instead of just letting go of it, I gave it some initial push? Well, in that case, the initial state includes both potential energy due to gravity and kinetic energy. So when we go through and it comes back at me, it has more energy total than when I was just letting go of it. And when all of that energy gets transformed into potential energy, it can now reach a higher position than where it was to start with. So in that case, I might be in danger, and I would not want to stand where I was standing. Of course, in reality, we did not account for friction, and when this demonstration is actually performed in real life, you see that not only does it not hit me in the face when I let go of it, but it comes a little bit short. So depending on how much of a push I gave it, I could rely on friction to actually dissipate some of that energy, and then it wouldn't hit me in the face, but that would be a lot riskier of a business than just releasing it. So what would be different in these graphs is that this column would not be empty, right? This work column indicating the work done by friction would have some amount of bar to it depending on how much friction was involved. That would go into accounting for where all the energy and work was being done. Okay, so hopefully this conceptual example helps illustrate the importance of thinking about how energy can change forms, and yet the total should stay the same or be accounted for example, in the form of friction. And so we have discussed energy both in terms of kinetic energy and potential energy, and we've discussed work as well. One thing that we have also said is that this potential energy we are talking about comes about by way of a force which is conservative. If the work that's being done on the object is being done by a conservative force, then it's associated with this potential energy. Specifically, the negative change of potential energy will be the work that's being done by this conservative force. So in reality, though, unless that force is constant, then, if it's changing along the path of displacement, really we talked about how you would need to add up all those little pieces of work in order to figure out what the total work is. And so that's tantamount to performing an integral along the path. And so if I just look at a small amount of work, dW, that's associated with du, then that's just the argument inside my integrand. And if I take this equation then and I solve for du dx, this is going to be equal to negative f. Okay, so what that's saying is that the derivative with respect to position of this potential energy is going to give me my conservative force. In other words, there's a relationship by which potential energy can be derived from a conservative force. So an example of this might be the potential energy related to a spring. If I take the derivative with respect to x of this equation, then I get back my familiar Hooke's law. So we did the opposite of this. We talked about how you could integrate this to come up with the potential energy, but you can do the reverse. You can know that this is the potential energy, and if I take the derivative, I will get the conservative force which is at work here, which is the spring force. So one question might be, by the way, this is how you would do this in 3 dimensions with partial derivatives. It's beyond the scope of the course to actually explore this, but I wanted to explain where this comes from. Finally, we might ask ourselves why there's this minus sign here. The minus sign, the negative sign, is there because a conservative force is always going to act in such a way as to try to push the system toward a lower potential energy, trying to reach the lowest potential energy that it can. And so this, another way to think of this is to discuss what we would call a potential energy well. So what you see here being graphed can be thought of as a potential well. Perhaps this is a graph of the potential energy due to a spring and the elastic potential energy, and how narrow this is, how wide this opening is, might have to do with the different K values. But you can see that it is a quadratic sort of parabolic shape. So remember that the conservative force is going to act to try to minimize this potential energy. And so let's consider this possibility. Let's say that I am plotting my potential energy due to a spring, and some particle is moving back and forth in its x position, and so this is showing me the potential energy that it has and the kinetic energy that it has at any point in time, whereas this line on top here is the total of the potential plus the kinetic energy. So as this say mass on a spring oscillates back and forth, it is going through this potential well like so. And so let's imagine that the particle is now at position 4, and we want to know what direction the force on this particle is pointing. Well, if the force is seeking to minimize the potential, then it's going to have to point towards the left, right? It's a little bit too high here. It wants to get back down to this position 3 where it's minimal. All right, what about position 3? Well, position 3, we have no potential energy at all here, and so the potential energy is at its minimum at this point. So at this point, the force is going to be equal to 0 newtons. And so one way you can think about this in general is to think about this as a slope. Position 3 is what we would call a stable equilibrium point, because at this position, the force, if you veer off in either direction from this position, it will point towards that position. So that's an equilibrium, a stable equilibrium point. If you were at the maximum of this function, or a function like it, then that would be something like an unstable equilibrium. So let's imagine now the particle is at a different position. If it's, say, at position 2 and it's moving to the right, what kind of acceleration can we expect? Well, acceleration points in the same direction as the force, and if the force is always seeking to minimize things, then it needs to go to the right in order to reach that equilibrium point. And so we can draw some general conclusions here that if the particle if you want to know if it's speeding up or slowing down, then you just have to ask which way it was moving to start with. So if it was moving to the right to start with, then it's going to speed up, but it will slow down if it was moving to the left. So you can imagine the thing again bobbing back and forth and back and forth, and as it reaches position 2 here, it's moving to the left and it's slowing, 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 and then it's coming back down, and as it's coming back down, it's getting faster, faster, faster. Okay, there are other types of potential wells that you may encounter. Here's a humorous one for your consideration, which was featured on PhD Comics, about the potential well that could explain why so many college students end up opting for cafeteria food. Of course, there are other potential wells in which there may actually be 2 minimum points. Okay, and maybe a particle will become trapped in the slowest one or this one that's slightly higher. In fact, gravity can be thought of in terms of a potential well. This might represent the potential well due to the Earth and things falling in towards the Earth and things becoming less and less gravitationally bound as I move away. And here's yet another example of a potential well. So with this last little bit about potential wells, we have discussed all of the different kinds of energy and depicted it in a number of different ways and done a number of different examples related to energy and work. But one thing we have not discussed is how quickly the work has been done, or how quickly the energy changes. For this, we need a new concept which we call power. So power is the rate at which work is done. And so because it is work divided by time, it has units of joules per second, which we now call watts. So the interesting thing is that you and I could perform the same amount of work, yet one of us could do so more quickly than the other and it would end up requiring us more power. If, for example, someone here was walking up the stairs at a slow rate of speed, that's not going to require very much power compared to running up the stairs. So in fact, let's do an example of this. We're learning this physics class remotely, but if you have encountered me at all on campus, you may have seen me running up the stairs because I like to wait till the last minute and run up the stairs to get to class. Other people, such as students in my class, may take their time and walk up the stairs. So this scenario is typical of what you would encounter if you observed us in a normal semester. So what I want to know is 2 things. Which of us has done more work in this scenario, and which of the 2 of our climbs required more power for us to complete? So the scenario is a typical student of mass 65 kilograms walks up the stairs and takes 10 minutes to do so. 1 minute to do so, 10 meters in height. I, on the other hand, mass 47 kilograms, run up the stairs in 25 seconds. So in terms of the work that we've done, it doesn't matter how quickly we've run up the stairs or walked up the stairs. All that matters is the work we've done against gravity, which is mgh. Now h is the same for us both. G is a constant, so that means that whichever of us has the greater mass has done more work. So the work of the student now is going to be greater than the work of the professor. On the other hand, power depends upon the time that has passed. Power is going to be the work divided by the time. So if I want to compare the ratio of the power that the professor was required of the professor as she ran up the stairs compared to the power output of the student, then this is going to be mass of the professor times g times h divided by time that the professor took. And all of that will be divided by the same thing for the student. Many things cancel here. The h's cancel, the g's cancel. Okay, and so this becomes MPGS over MSTP. And if you plug in the values that are given here, you should find a ratio of 1.7, meaning that my power output was 1.7 times the student's power output. In other words, it required more power of me to run up the stairs compared to the student climbing the stairs. So that concludes Unit 3. In our next lecture, we will start with Unit 4, where we will begin to discuss momentum.